Hello everyone, I am Anuj from BSc Chemistry Honors final year. Today I am preparing a audio recording for visually impaired student on the topic of Raman spectroscopy. It is a special type of spectroscopy which deals not with the absorption of electromagnetic radiation but deals with the scattering of light by the molecules. It is observed that when a substance, which may be gaseous, liquid, or even solid, is irradiated with monochromatic light of a definite frequency, a small fraction of light is scattered. Relay found that if the scattered light is observed at right angle to the direction of incident light, the scattered light is found to have the same frequency as that of the incident light. This type of scattering is called relay scattering. Professor C.V. Raman of Calcutta University, however, observed in 1928 that when a substance is irradiated with monochromatic light of a definite frequency, the light scattered at right angle to the incident light contained lines not only of the incident frequency but also lower frequency and sometimes of higher frequency as well. The lines with lower frequency called Stokes lines, whereas higher frequency are anti-Stokes lines. Raman further observed that the difference between the frequency of the incident light and that of a particular scattered line was constant, depending only upon the nature of the substance being irradiated and was completely independent of the frequency of the incident light. If P1 is the frequency of the incident light, then Vs that of the particular scattered line. The difference is called Raman's frequency or Raman shift. Thus, the Raman frequency observed for a particular substance are characteristic of that substance. The various observations that thus made by Raman constitute what is Raman effect, and spectrum observed is called Raman spectrum. Thus, in a simple way, Raman spectrum may be explained. Explanation for observing relay line and Raman line. When the incident photon hits the molecule, this collision may be elastic or inelastic. Elastic collision means that the colliding particle will return with the same frequency. Thus, the scattered photon has the same frequency as that of incident photon. This explains relay scattering or relay line. However, if the collision is inelastic, still the law of conservation of energy will hold good. That is, total energy before collision and after collision must remain same. Thus, some energy may be transferred from the incident photon to the molecule so that the scattered photon has lower energy and lower frequency than that of incident photon. This explains the occurrence of Stokes lines. Alternately, some energy may be transferred from incident photon to the molecule so that the scattered photon has higher energy and hence higher frequency than that of incident light. This explains the occurrence of anti-Stokes lines. This explanation may be further elaborated. When the photon strikes the molecule, the energy is observed by the molecule and it gets excited to some higher energy level. Now, if it returns to the original level, it will emit the same energy as absorbed and thus we have relay scattering. However, in most of the cases, the excited molecule does not return to the original level. It may return to a level higher than the original level, thereby emitting less energy than absorbed. This explains the occurrence of Stokes lines. Thus, a part of the energy of incident photon remains absorbed by molecule, so that molecule has higher energy than before. Alternately, the excited molecule may return to a level lower than the original level. Thus, more energy is emitted than absorbed. This explains the occurrence of anti-Stokes lines. In case of the molecule has less energy than before, the different cases may be represented diagrammatically. Levels. Polarization of molecule and Raman spectra. The Raman effect arises on account of the polarization of the scattering molecule that is caused by the electric vector of the electromagnetic radiation. The induced dipole mu depend upon the strength of the electric field E and the nature of the molecule mu equal to alpha E, where the alpha depends upon the nature of molecule and is called polarizability of the molecule. Thus, polarizability is the ratio of the induced dipole moment to the strength of the electric field. In case of the atom or spherically symmetrical molecules such as CH4, SF6, etc., same polarizability is induced whatever be the direction of the applied electric field. They are said to be isotropically polarizable. Such molecules are said to the isotropic molecule. In case all diatomic molecule or non-spherical molecule, the polarizability depends upon the direction of the electric field. Types of molecules showing rotational spectra. A molecule scatters light because it is polarizable. Hence, the gross selection rule for a molecule to give a rotational Raman spectra is that the polarizability of the molecule must be anisotropic. That is, the polarizability of the molecule must depend upon the orientation of the molecule with respect to the direction of the electric field. Hence, all the diatomic molecule, linear molecule, and spherical molecule gives Raman spectra. That is, they are rotational spectra active. On the other hand, spherically symmetrical molecules such as CH4, SF6, etc., do not give rotational Raman spectra. They are rotational Raman inactive. In in fact, this is one of the reasons for importance of rotational Raman spectra over infrared spectroscopy, because the latter require that the molecule must have a permanent dipole moment, whereas the former only requires the polarizability of the molecule must change during vibration. Explanation of Raman effect in terms of polarizability. The polarizability alpha of the molecule that is rotating or vibrating is not constant but varies with frequency of vibration or rotation. It is the sum of two parts. Equilibrium polarizability alpha naught, that is the polarizability when the atoms of the molecule are in their equilibrium position. The sum of polarizability of the molecule due to the various rotational or and rotational motion, each term depending upon the frequency of rotation or vibration. Thus, alpha equal to alpha naught summation of delta alpha n by del r into del Rn cos 2 pi Vnt, where alpha n is the polarizability associated with the nth rotational or vibrational mode and Rn is the maximum displacement of the atoms involved. Further, the electric vector of the electromagnetic radiation varies with time in a sinusoidal manner as E equal to E naught cos 2 pi V naught t. Substituting the value of alpha and E from equation 2 and 3 in equation 1, we get mu equal to E naught alpha naught 2 cos 2 pi V naught t plus summation of del alpha n by del r Rn cos 2 pi Vn t cos 2 pi V naught t. This expression consists of three terms. The first term as the frequency of the incident radiation and represent Rayleigh scattering. The second term contains and represents Stokes lines, whereas the third term contains V naught plus Vn and represents anti-Stokes lines.